Welcome. In this video, we are going to take a look at electron orbital energies for elements with Z protons. Okay, so we're dealing with energies. So let's write down the kinetic energy. And Ke is equal to 1/2 the mass times the velocity squared. And so this is for the electron, so we will use the mass of the electron times the velocity squared. The electric potential energy for the electron is going to be minus Q sub E times the potential. Okay. The potential is going to be due to the nucleus at the location of the electron. And so let's write, and the potential is going to be, okay, so we have a K, then we have the charge. For the nucleus is going to have Z, and we can use Q sub E. So Z times Q sub E, and that's because the charge of the proton, Q sub P, equals the magnitude of the charge of the electron, Q sub E. Okay, then we're dividing by how far away from the nucleus we are. That's going to be R sub N. Okay, and so the PE, or electric potential energy, we've got a minus. We've got a K, we've got a Z, we've got a QE times a QE, so Q sub E squared divided by R sub N. Okay, so the energy at N is going to be the Ke plus the Pe. Okay, so substituting for the Ke and the Pe, we get 1/2 mass electron times velocity squared. Then we have minus K, Coulomb's constant, times Z, Q sub E squared divided by R sub N. Okay, earlier we found when we equated Coulomb force with centripetal acceleration, mass times centripetal acceleration, that we had Z times K, Q sub E squared over R sub N squared. That was M sub E V squared over R sub N. And so we see that M sub E V squared is equal to Z K Q sub E squared over R sub N. One of those R sub N's canceled. So we can substitute this for M sub E times V squared. So we have E sub N is 1/2. Now we will put in our Z K Q sub E squared over R sub N. Then we have minus the K Z Q sub E squared over R sub N. Okay, so the order of the K and the Z doesn't matter. So we've got a half minus a whole. That leaves us a minus half. And so E sub N is minus 1/2. And let's just write, we'll go with the Z K Q sub E squared over R sub N. Okay, and we found previously that R sub N, and I'll link the video where we showed this, R sub N is N squared H squared divided by Z. We've got 4, we've got pi squared, mass of the electron squared, times K Q sub E squared. So we can substitute for the R sub N, and note we're dividing by it, so we can flip that fraction upside down. So we have E sub N is minus 1/2, And I'm going to write everything down but the r sub n first. So we've got the z, the k, the q sub e squared. Now we're substituting for the r sub n. So we need to write the numerator down here because we're dividing by r sub n. So we've got n squared, h squared. In the numerator, we've got z, 4 pi squared, m sub e squared, k, q sub e squared. Okay. And now we can pull out all the constants. Let's group them first. So e sub n, keep the minus sign. We're going to have a z squared. And we're going to have an n squared. Okay. And that is going to leave. So we've got, let me highlight. We've got a k and a k. So we've got k squared. We've got hopefully this color shows. We've got QE squared and QE squared. So that gives us a QE to the 4th. We've got a 4 pi squared, but we've also got a 1/2. So that's going to leave 2 pi squared. And then we have an m sub e squared. And all that's left is an h squared. So let's just double check this. Okay, so looking at the line above, we've got the 1/2. We'll go with the 4. Okay, then we've got the z here and here for z squared. We've got the n squared. Okay, we've got the k squared. We've got the QE to the 4th. When I canceled that, the 1/2 and the 4, that left behind a 2. And so now we've got the 2 pi squared, me squared, and h squared. Okay, so we've got it. We've got it. Everything looks good. All right. Now, everything in the parentheses, these are all constants. And it goes to e sub 0. So e sub 0 is k squared QE to the 4th 2 pi squared m sub e squared over h squared. And when we compute all those constants and convert to EVs, we get 13.6 EVs. And so we have E sub n is minus z squared over n squared times E naught. And we have the E naught is 13.6 electron volts. Okay, so the En is negative. Let me just go to a new page. E sub n is negative. And that is because the electron is bound to the nucleus. So since the electron is bound to the nucleus, so we need to add energy to liberate it. Okay. And so now, let me just write it again now. En is minus z squared over n squared times E naught U naught is the 13.6 electron volts. Okay, so now as n gets bigger, we see the En gets smaller and it gets closer to 0. So E sub n gets closer to 0. And this, when it does become 0, it would be a free electron with 0 kinetic energy. And that is also because as n goes to infinity, the potential goes to 0. And so we can say 13.6 electron volts is needed to ionize the electron from hydrogen. So, and that's the positive 13.6. So that's how much energy is needed to ionize the electron from hydrogen. Okay, and that has been verified experimentally. All right, and so we know delta E is HF, and it's also E sub I minus E sub F. And we can substitute, and we're going to substitute the E sub n is minus 13.6 electron volts over n squared. Okay, and this is just for hydrogen now. Okay, and so we're going to get HF is going to be minus 13.6 EVs over, and this will be n sub I squared. Then we have minus, and now this will be E sub F. We will have minus 13.6 electron volts over n sub F squared. Okay, so let's pull out a third. So HF is going to be 13.6 electron volts. Okay, we're going to be left with 1 over n sub F squared, right? We have minus minus, so that side's positive, minus 1 over n sub I squared. Okay, let's divide both sides by H times C. So we have HF over HC is 13.6 electron volts over HC. 1 over n sub F squared minus 1 over n sub I squared. And now we know C equals lambda F, right? We're canceling our H's here. And let's put, and C is lambda times F. Okay, so we have F over lambda F is 13.6 electron volts over HC times 1 over n sub F squared minus 1 over n sub I squared. Okay, so our F's are canceling. And 13.6 electron volts over HC is equal to R. So we have 1 over lambda is R times 1 over n sub F squared minus 1 over n sub I squared. And this is what Balmer found. Okay, so these are downward transitions, and that's because n sub I is bigger than n sub F. And this all came about by assuming L is quantized. And so there's the explanation for the hydrogen spectrum. I hope you found this helpful. Thank you for watching, and I'll see you in the next one.